Hi, everybody. Um, Good morning and good evening, based on where you are. So today we are going to go through the most in-demand skills for machine learning and AI, and also we'll be taking a look at an expert of my book, where I'll cover a lot of topics in this regard. So primarily, if you want to launch your career, you can launch it in Python or TensorFlow or PyTorch and R. It depends on your background. If you're coming from data analysis background, or you're coming from statistician background, or you're coming from mathematical background with programming, it depends on your skill set. You will be able to choose your particular skills, and then you will be able to launch your career. So just I'll give a brief introduction before we get started, and I'll go into the excerpt of my book. So primarily, as you're aware, that QuickStart has partnered with several universities, and they have been doing this certification for over decades. And now they have launched this initiative to sharpen the skills of data science practitioners, if you are, and if you would like to advance your career, or completely beginners who would like to pursue this path based on their backgrounds of different programming and different insights they have, performing analysis. And there are also several jobs available to this extent. I'll just give a brief introduction about me, and here is my background here. So I have overall around 22 plus years of experience, and around 10 years of experience in AI research and development. And I covered a lot of industries, implementing applications for them, building apps, and building several scalable infrastructure applications for aerospace, manufacturing, semiconductor, AFS, media, entertainment, automotive, CCS, customer care services, banking, energy, retail, high-tech, life sciences, chemicals, computer science, supercomputing, CPG, and high-performance computing. And I also authored a few books earlier, and this is the latest book that we will be going through today that will help you to launch your career. And so let's go through that. And so where's my other PowerPoint? Okay, here. So we're gonna, so this is actually part of my book, which I'm going to leverage today as our presentation. And so, I mean, if you're gonna sign up, you're gonna receive a copy of this anyway, but it would be more useful, if you go through it interactively so that you can understand and you can implement all of these, neural networks and, how you can advance your career. As you know, that Python has been the most popular programming language for 2021. And if you look at TOB programming index, or look at Redmonk programming index, any number of programming indexes that you can look at. So primarily, you will be able to gain, what is there in the market in terms of the positions that are available. And also, you don't have to worry about finding a position. QuickStart will also help you in finding the positions as well after you get certified with data science and machine learning, depending on your interest, and you will be able to find a position through them as well. So the most important thing for us to launch our career is moving from the traditional IT, which is basically information technology, where the way of doing things is different versus what we are doing with the machine learning and data science. So primarily any particular intelligent system that you're building will require some sort of high precision and best performing AI systems. And for that, the fundamental building blocks would be, to build neural networks. Of course, you can also, implement several machine learning algorithms without neural networks, but neural networks primarily will allow you to implement large-scale data sets that you would need to process, whether you're adopting supervised machine learning or unsupervised, or you're also doing semi-supervised. and reinforcement. And because many corporations primarily provide you label data, and if you're dealing with label data, then you would be leveraging neural networks to process your inputs and come up with the outputs. And you also have different types of hidden layers, and the hidden layers primarily contain the neurons, and then you're going to basically see how these nodes are connected neuron to neuron, and then you're going to apply and get summation of each weight, and based on that weight you also consider the bias, and you will be able to calculate the output for each node, and that's what actually will propagate throughout the neural network. And again, back propagation is to avoid the error, because you're going to randomly initialize these neural networks, and you will also be able to assign weights for each of these, but there will be some error. So in order to avoid, you can apply back propagation through calculus. We also take a look at it to see how we can do that. And so primarily, so this is basically your neural network, and each neural network will have a threshold value as well, and the data gets passed from node to node, layer to layer, and then that is going to, you can have as many hidden layers you want to define. It doesn't have any limitation, and you can even build thousands of hidden layers if you're doing deep reinforcement learning, like for example, something like Atari games. Some of the DeepMind laboratory, OpenAI, reinforcement learning, robotic environments, they created thousands of layers for the hidden layers to process all of this data and produce the outcome in a calculated way. So also you need to make sure that you're not going to create any problems in terms of your data models that you're building. You need to avoid any underfitting and overfitting, and you primarily need to be able to optimize through hyperparameter configurations of each neural network. That way you can get your output. So again, as we just saw here, just initializing the neural networks itself will not help us to perform the weight summations. You also would need to activate the neural networks. So each of these neural network you are going to activate leveraging several different activation functions. And some of the programming languages, like for example, if you're going through PyTorch already has a built-in function, for example, like ReLU, rectified linear unit. So you can simply apply the rectified linear unit function, and that will do the activation. And some other programming languages, you are going to have to do a lot of coding to do that, but if you have a built-in function, it makes life easier, so that you can simply apply that. And again, what is a ReLU? So ReLU is basically, you can leverage that function to activate any neural network. And it also, if you're going through the traditional way of activating through logistic regression, or applying a sigmoid functional, and you're also doing hyperbolic tangent function, or you're doing tan. All of these techniques may create some problems you may experience with vanishing and exploding gradient issues. So in order to, basically reduce that type of issues, you can go for the ReLU, which is a rectified linear unit. And when you activate that, it is going to solve your vanishing and exploding gradient issues, which you don't have to again explicitly code and program, and then you're going to have to resolve all of that stuff. So that is where it is very helpful for you to do this. So basically, you can apply a sigmoid function to activate a neural network node. Each node you're going to activate, and you're going to do a linear transformation, and that is complete when you activate it in a hidden layer. And a sigmoid function performs also a nonlinear transformation with activation function or a transfer function. And again, when you do the nonlinear transformation, your value is anywhere between 0 to 1. And that's how you know whether you're able to do the transformation of your neuron, and then you're able to activate or not. And so the other way of doing it is also through the hyperbolic tangent function, also known as tan. And this can be leveraged, and again, is not so completely different from your sigmoid function. It's very similar to your sigmoid function. The only difference is being that it's a scale function of sigmoid function, And also the difference is that ranges, it can be -1 to 1 instead of 0 to 1. It can have pretty much steep derivatives, and it might also create some vanishing and exporting gradient issues as we discussed with sigmoid issues. So that's why you would want to go through ReLU function to avoid any such issues if you are manually activating it. So again, let's take a look at the architecture of this neural network and understand, how you can apply your, weight summation and a few of the other activation functions. So here, let's see that in this neural network, we have input layer, we have a hidden layer and an output layer. So the input layer primarily consists inputs, Z1, Z2, Z3, and the hidden layer consists of primarily C1, C2, C3, and also it has weights. Basically, you calculate the weights there. Then you're going to produce an output. And so when you take the input Z1, Z2, Z3 and apply to the weights, then you're going to apply the ReLU function and activate the neuron subsequently on the weight summation. Then you can see this is what's going to happen for each of these. And so basically, you're going to calculate that, and that weight is what is going to tell you what is the calculation that you're getting. So now let's take a look at some of the programming languages. For example, we're going to start with TensorFlow, and TensorFlow and PyTorch are recent programming languages. Python has been there for a couple of decades. But the TensorFlow and PyTorch has made a lot of things simpler, especially if you're working on high performance computing and you also are dealing with heavy mathematical operations. It makes things easier for you to either work on a TensorFlow or you're going to work on a PyTorch. And also, if you're doing MPI, message is basically a parallel interface for parallel computing, and it will reduce any programming complexities, but also there is a C++ programming, snippets of code you need to write. So break down chunks of code and then parallelize and distribute on multiple, CPUs or GPUs, depending on your device that you have. So most of the reason, a lot of people go for TensorFlow in corporations is because, it's pretty good in mathematical computations and numerical calculations. And it also builds a data flow graph, and it will allow you to represent n-dimensional arrays. So it's not like it doesn't have any limitations. So each array also you can call it as a tensor, and that is primarily the central unit of communication that happens between the nodes. And each tensors you can consider as n-dimensional arrays that are immutable. So in Python, you simply have arrays like NumPy with leveraging the library NumPy package. And so you have a data type that's called dtype. And coming to a tensor, you cannot update the content of the tensor that you created, but you can create a new tensor for it, and you have different various types of data types available in TensorFlow. So you have TF float 16, which is a half precision floating point. And you have various types of data types available. So it all depends on what type of data type you would like to activate, especially if you're dealing with, plasma turbulence or nuclear fusion. It depends on the high performance computing project, how big you need the numbers to be, and whether you need them to be quantized or you want to basically go with the floating numbers or double precision complex numbers. It all depends, but it provides you all sorts of data types for you to perform all your computations. So now let's take a look at a little bit of linear algebra before we get into calculus portion of it. And so tensors, as we discussed, are basically, it contains several data types. As we have seen, we can have strings that represent text, or you can have integers, you can have floats. Depends on the type of calculations you are performing. And so now let's take a look at it. Let's break it down into multiple components. So you have multiple tensors and rank 0 tensor, rank 1 tensor, rank 2 tensor, rank 3 tensor. So let's represent the rank 0 tensor as scalar. So what is a scalar? So primarily, a scalar is nothing but it represents the quantity of measurement of a number. that contain a single value in the tensor. So anything that you would like to compute for a single value. So for example, you want to compute the mass of a particular object, or you want to measure the distance, or you want to measure the speed or temperature. All of this you can simply represent as a scalar, and you can also represent with either a positive or a negative magnitude of the quantity, and so it is represented as the 0th order of tensor or rank 0 tensor. And and Z is part of the data set R, and so the data set R is primarily that represents the real values, and Z is basically a scalar that is part of the data set. So now let's take a look at this example that we're going to create, and we create a scalar of the 0th order tensor rank of string, and 16-bit half precision floating point, and 64-bit double precision floating point, and a constant value. So anyway, you're going to get all of the programs through my book, not to worry right now, how you're going to get these programs and stuff, so that you're going to get through my program, and you can practice each example, and you can refer to each data type and what it means and what you're computing. You're going to gain all of that from the book. So again, now we're going to go for a rank 1 tensor. So rank 1 tensor is primarily a vector. So a vector is basically that comprises a list of values, and it can contain both magnitude and direction as well. So in the previous case, you're seeing most of the quantity measurements we are dealing with magnitudes, and the rank 1 tensor, you can also represent the direction as well. And so primarily a point in space is represented by a number mapping the point in space. So you look at X axis and you also look at Y axis, and you're going to have a vector represented. For example, we're going to represent the vector as 3, 9, and so you're going to represent this on a scale of X and Y plane. So where X is 3 and Y is 9. Okay, so now you want to do a calculation of this magnitude. You can apply the Pythagorean theorem. I will provide you X and X plus Y2 is Z2. So if you're going to represent that, so basically 2 plus 2 is 3 square and 9 square, and the square root of it, which is 9.4. So the vector rank 1 tensor can contain more than 2 values, at least an array. So if you're dealing with, again, Python with a data type D type, then you're going to have multiple arrays you can declare leveraging the package NumPy. And you can, so the book I've broken down into multiple different ways. So for natural language processing, I've written the programs in Python. For linear algebra and calculus, I've written the programs in TensorFlow. And for reinforcement learning, I've written the programs in PyTorch. And again, for applying any statistics and applying any specific, multinomial regressions or polynomial regressions or logistic regressions, most of the statistics, I also created these programs in R. And again, your conventional machine learning algorithms like naive Bayes, or you're also dealing with decision trees, random forest, I also have written in Python. So you're going to get, basically programs in multiple programming languages, so that it depends on your background. If you're a statistician, you're more comfortable with R, you can certainly go with R, and that helps you to achieve your outcome, to help aid your background as a statistician, and advance your career as a machine learning engineer in R, representing all your machine learning models, and that will help you to launch your career in R. And if you're more comfortable with, if you're more comfortable with Python because you have a lot of programming background, maybe you're coming with programming background of Java or JavaScript, and you are completely aware of object-oriented, concepts, and you're able to do that, then you can certainly go and write your programs in Python. And again, if you're running your programs mostly, in the advanced programming languages like TensorFlow and PyTorch that have been actually, created to simplify your mathematical operations and your data visualizations with TensorBoard, you can go for TensorFlow or PyTorch. Again, the beginning there were a lot of differences between TensorFlow and PyTorch, but now they're very close in terms of the way they function and they operate. So again, you can choose what you would like to choose depending on your, your preference and your programming background. Again, we just went through the rank 0 and rank 1 tensor, and from again rank 2 tensor makes things more easier for you. Is primarily like a rectangular array, and you can represent a number of second order tensors and others. So if you're going to declare a tensor, a rank 2 tensor with a matrix x and y, and then you're going to represent them with x and y, x rows and y columns, and that is what you're going to do. And let's say we're going to create a matrix with 3 by 3, and in 3 by 3 you're going to represent different columns. So for example, in this case we have 3 columns and 4 rows, or you can keep 3 by 3 just this G10, Z11, Z12, Z20, 21, 23 to 32. So when you do this primarily, you're going to declare, and then you want to perform any computations, right? So you can perform any computations on a tensor, especially on a rank 2 tensor. You can do multiplication, you can do division, you can do deduction, any such operations. For that, you need to be able to shape a tensor, and how many elements you want to have. You can list out the number of elements first of all. So you're going to print and see these are the elements, and then you can perform your mathematical computations, or you can also perform any other mathematical operations in the tensor. Again, so in order to shape a tensor, you have a syntax called tensor shape, and that will help you to print the output, and that will give the rank 2 with shape 3. And again, you can also change the shape of a tensor, and so that actually will help you to, this is a great utility you have in TensorFlow, and if you're using the tf.once is a built-in function, and basically what it does is it creates a tensor, and it defaults the values of all of the tensors to 1. So you simply create on the fly, and just say tensor underscore 1, for example, is a tensor I want to create of a rank 1 tensor. All I do is I say tf.once, and then I just declare the number of elements in it, and then I'm going to print. It's going to just default based on I'm saying, okay, here is what I want to create. I want to create these elements, and that is exactly you're going to define as your shape, and then you default it to tf1s, and it's going to initialize with these values. So that is a good function that you can leverage. Again, you can perform matrix multiplications, and you can define the tensors, a rank 2 tensor, with a 4 by 5 matrix, a bit complex than the rank 1 you've seen with 3 by 3. And you can also, if you do manually this calculation, and this is what you're going to get by multiplying each of these, matrix A and matrix B, you manually multiply, and that's what you're going to get, 3 by 2, and you get 9 by 1, and so on and so forth. You keep on multiplying each of these element, and so that's what you're going to get. Now you can also do it with the programming, and all you do is simply run through this TF tensor programming, and you will be able to declare it initially with the TF constant, and you can even hard code with TF constant what are the elements you want to pass, and then you just shape the tensor with what is the shape you want, how many rows, how many columns you would like to represent. So that's what gives you the, that's what shaping a tensor is. And then you're gonna perform your calculations as we did manually just now. So you're gonna do a 3 by 2, 9 by 1, 6 by 4, and 4 by 6. That's what's gonna give you 63. So again, programmatically, you can do this much more simpler. You just multiply both tensors, and the matrices get multiplied, and you'll get the results. This will be the result that you're going to get from this multiplication. Okay. So now coming back to, there are a lot of mathematical applications that you can apply in the linear algebra. So for this presentation, I covered a few of those, but you get more extensive when you actually are able to set up your Jupyter lab, and then install your TensorFlow, install your PyTorch, and then install Python. And again, I'm not going through the installation process during this presentation, but you can do that. You simply download from Anaconda, and depends on what system you have. You have Mac OS or Linux or Windows, doesn't matter which particular operating system you have. Anaconda provides the Jupyter Lab for all of them. So all you do is you go and you download the Anaconda, and then you set up your Jupyter Lab environment, and then you can start creating your Python notebook, or you can start creating a PyTorch notebook or TensorFlow. And for R, there is a little bit of configuration you need to do to make it work in Jupyter Lab. But if you don't want it to be too complex, what you can do is you can primarily go into, just install RStudio. It's mostly available for Mac OS as well as for Linux, as well as for Windows. Whichever the operating system that you have, simply download it, and then you can start writing your programs in R, and then you can get your outputs. It has a so every possible operation that you can perform to get your charts, everything displayed. So again, if you're in PyTorch, you're going to have to display your data visualizations through matplotlib, which is a library of Python. You're going to still leverage that. You do an import of Python, import of matplotlib, and then you're going to start representing your graphs through that. But if you're familiar with TensorFlow, you can also get all of your plots and your graphs you can display through TensorBoard, which is a data visualization dashboard. So, I mean, I don't think there will be sufficient time to cover it all, but I actually have created YouTube videos for each of these topics. So you can just go to YouTube and just type GP Pulipaka, and you will find a channel, and you go, you'll get a coverage of each topic from me, and I will be explaining the background of this and what you're trying to achieve and what is it you're trying to get. But primarily at this, in this presentation, I just would like to get you familiarized with the type of programming languages we have, and what are the capabilities and what you can actually do to launch your career, because you'll be writing a lot of programs for your organizations, and what are the things that you can actually implement. And again, if you're working for some national laboratories like Sandia National Laboratory, or you're working for Lawrence Livermore located in San Francisco, they are all into high performance computing. And it's a heavily with multi-grid algebraic methods that you need to apply, vector calculus, various types of computations you're going to perform to optimize their, plasma turbulence or nuclear fusion. So for that, it's very important that you have a greater foundation that you can build in terms of, leveraging all the mathematical applications and operations that you can perform. And that will help you to, each of these topics I'm also covering as part of upcoming conferences. So there's another conference upcoming right now, EVER conference. And then again, there is another conference called Data Sci Connect. And also conducting a few more conferences for world's largest IoT Premier Congress from STAR conferences. So I'm actually taking each topic and breaking it down there, and you'll also be able to get some demos and stuff. So that is where you will get a more deeper dive into these topics. But right now, I'm just gonna walk you through, the topics that you need to be familiar with, and what are, how these skills will help you to launch your career, because it just gives you a glimpse of what is required for you to be successful in launching your career. Okay, so again, singular value decomposition, and that is, again, so this is a fundamental building block, and a lot of companies are building recommendation systems. Like for example, if you're Netflix or Amazon, all of these companies leverage a singular value decomposition. So the reason why I call it the billion-dollar algorithm, the multi-billion-dollar companies are simply surviving on this algorithm, as I mentioned, all the recommendation systems, all of these streaming systems, or if it is a book based publisher. So how when you're going to shop, you purchase a book, or you're going through it, you start seeing some recommendations. They're going to tell you, oh, you need to pick up this book. How would they do it? So I'm going behind the screens here, rather than the business context, more of a technical context of how it will help you to, that you build this, these type of algorithms and these type of mathematical operations. So that's what you can do actually when you, sign up for a QuickStart, and then you are able to learn TensorFlow, PyTorch, Python, and R. That will help you to perform and build all this sort of algorithms for you. And I have written extensive examples for you with complete programming. It's not just like, I'm going to give you the entire behind the scenes of how it works, and then the logic and the mathematical operation, but you will be able to actually do it in your program and get your results. So this is going to be a demo from the book, and not just something like, you're going to walk away understanding only the concepts, but not able to be able to implement. You will be able to implement, and you will gain complete fundamental building blocks of all of the operations from TensorFlow, PyTorch, and R and Python. You can do the natural language processing, you can do the machine learning algorithms and reinforcement learning algorithms, and also deep learning algorithms. Okay, so now coming to calculus. So calculus, again, it holds a vital role in performing numerical computation. So no matter what your field you are in a scientific field, you want to calculate the aerodynamics, or you want to calculate the flow velocity or the viscosity, or when you're in high performance computing, you need to be able to calculate all of that, right? So that will help you. And again, so calculus is a fundamental building blocks for supercomputing field, where you can apply this, and you can, it basically, the rate of change between a variable to another variable is what is calculus is all about. So the rate of change in a function can be estimated by the calculating rate of function y to the change in the independent variable x. So that is in a nutshell what calculus is all about. So now coming to, again, you have a lot of like built-in libraries available. So if you're doing a backpropagation through Python, right? So you will have to perform a lot of calculations. You have to estimate the total calculation loss, total calculation error, and then you run through multiple episodic iterations to reduce your total loss and error, and then you're going to minimize. It may appear that loss is very less when you're doing this, but when you're actually running through this, you will see that when you run through multiple episodes, the loss is significantly reduced, and it will improve the performance of your neural network. And for that, again, you can do the AutoGrad. Basically, is a library from PyTorch, where you have functions already built in for performing your backpropagation or forward propagation, and you also have to do the backward pass, you have to do a forward pass, and that will give you the automatic differentiation. And again, this is something you can do it in PyTorch and TensorFlow much easier, as opposed to be doing it in Python, because Python, there are not a lot of functions that are built in and available. So that's why you would need to. So that's what I'm highlighting here. So there are neighbor implementations of automatic differentiation with TensorFlow and PyTorch. So that is where it can actually help you. So the AutoGrad package of PyTorch will help you to perform a forward differentiation and a backward differentiation. So that will pretty much give you the entire backprop in no time, so that you can actually reduce your errors. You don't have to actually run through a lot of programming, and you can reduce that. So again, Jacobi matrix and Jacobi determinants also have covered. It's a different type of, you know, um, uh, way of dealing with mathematical operations. And, you can represent the variable x as g of uv or y of huv, and it can be represented as a 2 by 2, um, you know, um, Jacobi and Jacobi matrix. So for example, A, B, C, D can be computed as A, D, B, C. So you're doing a differentiation for each function. So differentiation of X, Y, differentiation of U, V is so primarily is going to be, a differentiation of X by differentiation U, and differentiation X by V and Y by U and Y by V. So these are basically the bars representing 2 by 2 matrix are determinants. And so again, you can take a deeper look at inner workings of automatic differentiation and how you can perform it. And that will give you, more insights on how you achieve the automatic differentiation leveraging. But again, the good news is that there's also, a API from TensorFlow called TF dot gradient tape. So the TF dot gradient tape will provide you the forward mode and reverse mode as well. So you can leverage these APIs. That's what I'm saying when you're doing with our TensorFlow. I have to write this all up manually, and TensorFlow just performs just like that because it has all of the built-in functions for you. And okay, so I give some examples of how do you compute this, and you can get all of that. And again, chain rule also have covered here, and chain rule also very crucial for backprop, and it will provide the differentiation for obtaining the derivative of the composite function. That is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. So we're going to represent with Leibniz differential notion here, and you can represent mathematically in this fashion. And you're going to apply this with continuity, and you're going to get your chain rule established as you differentiate this continuously with limit declared. And again, you can take any create a tensor 1 or tensor 2 or any of these ranked tensors, and then you can start applying this differentiation on that matrix, and that will help you to apply your differentiation on the matrices, so that you can apply the chain rule and you can get the results that you want. So again, as I mentioned to you, for implementing backprop in Python is a bit complex compared to implementing in PyTorch, because you can leverage the auto differentiation and auto grad package to do that. And if you're doing it in Python, let's say that we're going to do this in Python, right? So let's say we're going to introduce now a neural network, and we're going to have this neural network with inputs as A1, A2, and then it's going to have hidden neurons as Y1, Y2, and then you're also going to get the output neurons as Z1 and Z2. So we're going to also assign 8 weights here, from weight 1 to weight 8. And so let's say this is how we're going to define this. And so primarily, you're going to have A1, A2, Y1, Y2, Z1, Z2. So you have multiple weights. Any place these nodes are getting connected is adding up to a weight. And also you can define a couple of bias nodes. And so here we are defining bias 1 and bias 2 nodes. And now let's initialize these weights with some values, random values that we're going to assign to each of these weights. And then we're going to take a forward pass, and then we're going to compute the total input assigned to each neuron. And then we're going to apply the logistic function. So logistic function also we can leverage to apply as an activation function to the neural network. So now we're gonna, when we do that, so net input y1 is basically nothing but calculating the weight 1 into a1 plus weight 2 into a2 plus bias 1 into 1. And net input y1, again, if you see the initialized values I have assigned here, and you're going to substitute those here, and then you're going to compute your net input. And similarly, you're going to do the same thing in the same pattern for net input y2. You're going to calculate, and you're going to get the net input y2. And then we're going to apply the logistic function as the activation function. And then you're going to get your output A1, A2 by applying the logistic function here. And then you're going to calculate your net input Z1 and net output Z1. So again, you're going to apply the logistic function to calculate your total net input and net outputs. And again, we're gonna apply here and find out the error, because every time you do this, you know, you're gonna getting some error. So we need to be able to calculate the total error and total loss so that you're gonna reduce this error leveraging the backprop. And how do we do that? So basically, let's say the error total is your summation of half of ideal target minus actual output square. And then you're gonna start applying, you know, you define this is what your ideal target is at 0.01. And then you're gonna define the ideal target for the other target as 0.99. And then you're gonna compute your total error. So this is the error you're going to get when you're, you know, computing these weights, and then you're passing through the neurons. So now, you know, primarily, you know, how are you going to reduce this total error, right? So the partial derivative of the total error you can represent as error total by differentiation of each weight. So when you wanna, we just talked about the chain rule. So chain rule is basically applied to differentiate a function of a function. It's not differentiating a function, but it is rather differentiating a function of a function. So for example, if you're trying to you know, find the value of cosine Z2, for example. So in contrast to finding the cosine value of Z, cosine Z2, what we're trying to do is we're finding the cosine value of Z2. That means primarily there are two functions here, f of Z and Z of Z, which we can represent. Let's say X is f of Z of Z. But that is a function of a function. F Z of Z is a function. Z of Z is a function, and f of Z of Z is a function of a function. And that is what is basically a differentiative function is. And you know, the reason is the G is the square function, and F is the cosine function. So mathematically, we can represent as F Z as cos Z, Z of Z as Z2, and F Z of Z is F of Z2 as cos Z. So then F Z of Z becomes cos Z and cos Z2. So in this case, what we're doing is we are differentiating the function of a function. So for example, we want to substitute Y as a Z of Z. And when we apply the chain rule that we just went through, then you're going to get, you're going to take a backward pass, and you can reduce the error as well. So now we are applying this chain rule for the backward pass. And basically what you're going to do is, in order to compute your total error by a particular weight, you're going to differentiate the total error by the output Z1 multiplied by differentiative of output Z1 divided by differentiative of net output Z1. And then multiply that by differentiative of net output Z1 divided by the weight 5. So this is, we are trying to here calculate the total error for weight 5. So this is what we have arrived. So you're thinking, okay, so this is the only error in this, you know, backward pass we are able to induce. No, the thing is that you can significantly improve it when you run through the iterations. It's gonna, you know, be minuscule. It's gonna reduce the total error to a certain extent that it is, you know, you already have overcome the problem of, you know, minimizing the error through your backprop.